Did someone chat? Or is that from a previous chat? Someone just said woot. So I've got to assume the woot means they found us.
Nice. Oh, hey, I found a dog.
Oh, good. Hello, Izzy. How's it going, Pamela? Oh, we can't hear her. You're muted, Pamela.
I turned off my microphone while I was munching my cup full of delightful, wonderful M&Ms that you didn't need to listen to me chomping on.
Product placement.
People are saying they hear voices, so I'm going to assume that we're live. Or people are crazy and they may want to go talk to a doctor. I'm going to say hi to Damien Reloaded, Dennis Tyus, Don Ankeny, Eric Knapp, Eric Schneider, Giselle Saberman, Guido Bibra, James Haney, John Suffield, Larry Beckham, Lillian Brennan, Lloyd Mountjoy, Michael Collins, MMDE, Nancy Graziano, Arjun, Sylvan Westby, Simon Love, Tech Tang, Tom Nafy, and Warbash. Hey, everybody. Welcome to Astronomy Cast. We're going to make you a show. Man, we're just got to give people a couple more minutes to settle down, have a seat. If you have no idea what it is that you have stumbled into, although I find that pretty weird that you don't know, we are going to be doing a live recording of our beloved Astronomy Cast show, which we've been doing for 10 years. This is our penultimate episode. So we're going to be doing for this season of this season. Yes. Yeah. Forever. So we're going to do this episode, and then we're going to drop our microphones, and then we're going to do another episode next week. And then we're going to take a break for 2 months and let our brains relax. And then we will pick things up again at just shortly after the beginning of September when you go to DragonCon and you do a live version of Astronomy Cast with some of our DragonCon friends.
Yes.
Yay! That'll be fun. So we will chat for 25 minutes-ish and do a show, and then we will stick around and we will answer your questions about space and astronomy.
That sounds good.
Yeah.
Could you give an audio test while we have an image up, just to make sure?
Sure. Pam, so we're going to put a picture in front of your face, and we want you to talk when we do this. So
one, there.
Maresy dotes.
That's good. We're good. We're good. You don't have to go through the whole thing. We're good. We see sound things going up and down, so I think that's good. And we definitely have her. Also, it's Chad's birthday.
Yay!
Chad,
Happy
of course,
birthday.
Chad, of course, is the engineer / producer / editor / cameraman who works with me on all the video projects, and he is now sitting right beside me. So one less thing that I have to do. Chad now does, which is great. Look at me doing the show with no hands. It's perfect. Someone says, "Is that a tarnished behind behind Pamela?"
TARDIS. There is a TARDIS.
You have a TARDIS behind you. Yeah.
Yes. There's so many weird things behind me right now.
Yeah, he said TARDIS. Are you going to be live broadcasting from DragonCon?
I won't know until they tell me the schedule. That's entirely up to DragonCon, so we don't always know in a timely fashion.
It's tough too. Like, just the internet is terrible.
Yeah.
It's not worth it. And so instead, DragonCon's great. They have an audio engineer for pretty much every panel that you do, and they give you a file of the panel that just happened. And so Pamela will turn the panel into a show through the magic of technology.
Yes. So we have a proposal in. It now just becomes a matter of does the proposal turn into a live episode?
What was the proposal? What was the topic? Did you?
I don't remember.
Okay. Yeah. Something.
It was something.
Okay, cool. Well, I'm ready. Are you ready?
Yes.
Do you have your recording software ready to go?
Yep.
Okay, cool.
You ready for me to press return?
If you're also ready to press record. Yes.
Yeah, same button.
Okay. Press record.
Ah, error while opening sound device. Okay, hold on. Let me
Testing,
close
testing. Is ours
Audacity.
working? Ours is working great over here. Good. We have good audio levels right here. Hello, Preston, for the second to last time. So
Except
stop it, and then we'll
Yeah.
we'll restart it. Yeah.
Okay.
While we wait for Pamela to figure out what's wrong with her computer, and then you can just
So it is-
hit the little X, and you'll down, lower, there.
There.
test. Okay, I'm now recording.
We are also
Catching up.
recording.
Okay, hi Preston. We're going to miss you.
Oh. Here we go. Astronomy Cast, episode 417. Expectation failed. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today. With me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
I am doing great. Just to let everyone know, this is the penultimate episode of this season of Astronomy Cast. So we have this episode, and then we have one more episode, title unknown, and then we will take the summer off as we always do, and then we'll be back right after Dragon Con in early September. So if you're like wondering why episodes aren't showing up on your podcatching software, that will be why. We'll be back. Don't worry. Don't cry.
So in looking at what would be possible for the next show episode, we've been taking somewhat advantage of the HTTP error codes since we hit number 400 because it's fun. And error code 418 is "I'm a teapot."
Whoa.
We need to figure out how to turn that into an episode.
I gotta, well, I mean, obviously we need to talk about some kind of like, quantum mechanics.
Tempest in a teapot?
No, like, well, either we could talk about sort of, anyway, there's a ton. Seriously, that is the 418 error code?
That's the
All right.
418
I love
error
it.
code.
I love it. I got a million ideas. We'll talk after the show. But got a theory? Great. Now go out and test it. Today we talk about what happens when you turn up the unexpected, from dark energy and relativity to the heliocentric model of the universe. So Pamela, today we're going to talk, this is sort of one of your recommendations, we're going to talk about when you have a theory and then you try to go test it out, and what happens when perhaps nature doesn't conform to what you were expecting, either in the good way or in the bad way. So let's go sort of all the way back to the beginning of, I guess, modern science, ancient Greek science, and talk about some of the first, sort of one of the first situations of this.
I think the best example of, well, that didn't work, was poor Kepler kept trying to come up with equations to map out the planetary motions, assuming circular orbits. And it turns out planets, they really don't move in circles. They move in ellipses, slightly flattened circles. And so there was a whole lot of expectation failed in terms of making careful observation, putting together the equations, predicting what should be seen, and not seeing it.
Right, but I mean, this is all sort of comes on the original model of the universe developed by Ptolemy, right? Was that the Earth was at the center of the universe, and that there were all these crystal spheres surrounding us, including the sun, and that all of these spheres would turn, and it would pretty well explain the motion of the universe. And then Copernicus flipped things around and put the sun at the center of the solar system and had the Earth just be just another planet. And that also made sense, but didn't it didn't predict,
it didn't work.
It didn't work. It didn't predict the motions of the planets
Right.
as well as the Ptolemaic system did, that people had been grinding away on for hundreds and even thousands of years. So And so you've got this expectation that all of the planets are going in these perfectly circular orbits around the sun. Didn't work. How did they get that resolved?
Well, so once poor Kepler figured out, and he started from the supposition that the Earth is not the center of the solar system. He did start from the Copernican notion that the sun is in the center. And because he was working from math, he eventually just had to have that leap of ingenuity, that leap of creativity to try a different shape. Once he tried an ellipse, suddenly everything fell into working. He could make accurate predictions of everything except for one annoying little world.
Which annoying little world?
Mercury.
Okay, so what was wrong with Mercury?
Well, it was our next expectation failed kind of problem. And this is Mercury is in so close to the sun that to fully understand its motion, you have to take into account not just Kepler's equation of motion, not just what Newton came up with to explain the extra pulls and tugs that become apparent that Newton was able to explain. But you actually have to have a relativistic correction to fully get at Mercury's motion.
Right, and they had no idea about relativity. So they did these really great observations of all the planets, got them all to within, really accurate points, but then Mercury just kept drifting away. How off was Mercury? Was it? Go ahead.
It wasn't a huge amount. In terms of Mercury's nowhere near where I expected to be. But it was definitely the star it's behind, or the star that's behind it, rather, is not the correct star by a small amount through a telescope eyepiece. If you were to very carefully watch Mercury year after year after year, you'd see that over the course of a century, it moved about 43 arc seconds off of where you'd expect it to be compared to the background stars.
Right. So you're sort of, with the other ones, you could say, well, maybe we're making some observational error, we're a little off, but Mercury was just completely not where it was supposed to be.
Right. And so this works out to about half an arc second a year, and good telescopes can make out 1 or 2 arc seconds. So over a matter of years, this becomes more and more and more noticeable, with more and more what the insert expletive of choice is going on.
So then how did they finally resolve that?
Well, for about 300 years, there was a whole lot of scratching of heads. Now, 300 years is a bit of an exaggeration, because it wasn't Kepler who immediately noticed the problems, because they were still working from not the best optical systems out there. And in fact, a lot of the work that he was working from, it wasn't telescopes they were using. It was very careful alignment circles, big old chunks of metal where they're measuring essentially with fixed sextants where things are on the sky. With that kind of technology, it wasn't Kepler who was noticing this in data taken by Tycho Brahe. But over the decades and centuries of telescopes, up until the early 1900s, when Einstein started working on his theory of relativity, which was able to predict and explain Mercury's precession. Mercury's not quite in the right place according to Newtonian physics. It was Einstein in the early 1900s that fixed the problem with our expectations.
Right, and so there was a couple of other experiments that they did as well around that time to confirm Einstein's theories on general relativity. In fact, they're still attempting to directly observe. I guess we've wrapped up the final Einsteinian prediction with the direct detection of gravitational waves, but it's just this sort of sequence of new kinds of observations that they were able to do to prove both the movements of Mercury as well as some of his other suggestions, these other
And
predictions.
and at a certain level, I think because relativity, like quantum mechanics, is so non-intuitive that it's going to be at least a few more generations, if not forever, that people are going, and we shall test general relativity in this new direction now, just to confirm one more time that your expectation is wrong and reality is much trickier than.
Have you ever heard that anecdote with Eddington, where someone asks him, "Is it true, Dr. Eddington, that you're one of the three people in the world who understand relativity?" And he stopped and thought for a while, and then someone's like, "What's wrong? No?" And he's like, "No, I'm just trying to think about who the third person might be."
I yes. when when I was at Harvard, we had a professor who was introduced to me as one of the two people that understood string theory in the United States, and I decided I didn't want to ask who the other one was.
Right. So we've got, turns out looking for circular movements of the planets, and it turns out they're ellipses and everything changes. And then trying to use those elliptical motions of the planets, and it turns out that they're under relativistic motion, and, sorry, but not sorry. So what's another example where you went looking for one outcome and you got a completely different outcome?
So again, at the turn of the 1900s, technology in astronomy was going through the second renaissance. We went from having telescopes to suddenly we started to be able to do amazing glass plate photography, and this brought on a whole new set of things that we were finally capable of doing with longer exposure times. And one of those things that we were finally able to do was take spectra to spread the light out through prisms or diffraction gratings so that we could see the individual emission and absorption lines produced by the atoms, the gas in stars and galaxies. And part of doing this included many different folks looking out at galaxies. And the expectation was that we lived in a steady state universe that had kind of been around forever, would kind of be around forever, was neither expanding nor contracting. It was just steady. And if you live in a steady galaxy, it was assumed that about half the galaxies would be moving towards us, about half would be moving away from us, and it would be this nice, friendly, random distribution. And it was a fellow by the name of Vesto Slifer working out at Lowell Observatory who was the first to notice, no, most of the galaxies, they're running away from us. Most of them have light that is shifted towards the red. And this meant that we were either in a special place that caused all the galaxies to run away, or we lived in a different kind of universe that we couldn't understand at that moment. Now the thing was, all he knew was the galaxies tended to be moving away from us.
Right. And so the expectation, the perfectly natural expectation that you would think of is that, you would imagine something else that you're familiar with, like imagine birds flying around you, or you're out on a boat and there's a bunch of other boats, and some boats are moving towards you and some boats are moving away from you, and some boats are sort of hanging out at the same distance, and by detecting those motions, you can start to get a sense of what's going on. And the completely unexpected result is this: all these galaxies are all moving away from us. What's wrong with us? Why do they hate us? Right? I'm sure it was a blow to his ego, but then, so what was the sort of understanding that they came to?
Well, so Henrietta Leavitt, working at Harvard College Observatory, figured out that you could use pulsating variable stars to measure the distance to, well, anything that had a variable star we could observe in it. So using Cepheid variables, Hubble the Hubble, Edwin Hubble, was with his colleague Milton Humason. They took glass plate spectra and images of a variety of nearby galaxies, measured the distance using those pulsating variable stars, those Cepheids, with what we now call the Leavitt relationship for their distance. And he made a plot of the distance to the galaxies compared to their recession velocity or their approach velocity, so their redshift or blue shift. And what he found was the more distant something was from us, the faster it appeared to be going. And it was the nearby stuff that had this random mix of moving away and toward us. And the way we now understand this, thanks to Hubble, who actually put the idea forward, is the nearby stuff, it's gravitationally bound to us. We're all kind of in this local group together. But once you look beyond our local group, we start to see things getting carried away from us by the expansion of our universe. And something that's nearby doesn't have that much stuff between us and it to do the expanding. But the further something is away, the more stuff is between us and it. And all that extra stuff, all of it's expanding, which means that further away stuff with more expansion going on is going to be carried away faster.
So, fine. That's all fine, Hubble, and obviously this led to the concept of the Big Bang cosmology and this understanding that the entire universe was once a singularity, and then it's been expanding ever since. Don't ask what came before the singularity. That is not a question that the Big Bang attempts to explain. But I know that just in the last, say, 20-ish years or so, right, astronomers tried to really get a good sense of exactly how fast the universe is expanding and exactly when it's going to slow down and stop.
Right. So back in 1998, and I think most modern professional astronomers have this year like etched into their brain, because in 1998, two different supernova detection experiments, two different groups of observers who were trying to measure the expansion rate of the universe by looking at supernovae that have really bright spectral lines that can be detected at these great distances, and which also have a standard brightness, because they're just explosions of a set amount of material. If you consistently blow up the same amount of star, you end up with essentially the same brightness of explosion. So by being able to measure the expansion rate using things with a set distance, yet again, they were trying to get at how does the expansion rate of our universe change with time? And the thought was that three different things were going to be happening. We were either going to slow down so much that eventually gravity pulled the whole universe back together and crunched us and we died by fire. Or perhaps the universe's expansion was going to ever just slow until asymptotically, which is a fancy math word for in infinite time, the universe essentially stopped. The final theory that we had was there'd be enough that while it was slowing down, it would never slow down so much that it stopped. These were the only things that we really even considered, because to consider anything else was to say that when you took the integral of one of Einstein's equations, you got an extra constant that changed the acceleration of the expansion rate, that it wasn't just a single rate forever, but that it was a changing rate over time. And all of us just wanted to set that constant to zero. It made the math lovely. But as Chris Impey once put it in a very strongly emotional talk, no one ordered this constant up, but the universe put it there. And what was found in 1998 was all of our mathematical assumptions that you could set this constant to zero were completely wrong. And our universe does indeed have an acceleration term, and that acceleration term is causing our universe to expand at an increasing rate forever.
Right. Thanks, Einstein.
Hey, the guys did get Nobel Prizes for it.
You know what I find interesting is that people don't like, people find that outcome, that, you know, the heat death of the universe, this accelerating expansion, this cold, quiet, long thing. I find people generally find that more sad and depressing than the big crunch, right? This idea that the universe is going to come to a stop and then it's going to come smashing in and everything's going to get mulched up. For some reason, they're like, that's the one they were hoping for, as opposed to the one that we've got. And I find that really weird, because
Well,
this one just gives us more time, you know, like,
yeah. But the big crunch, it's like we get to see everything later. It's like a reverse diaspora. Everyone comes back to visit and then
yeah,
kill you.
yeah, yeah. So okay, so there's dark energy completely, and it really is the classic. I mean, it is the gold standard of completely opposite results that came from doing some kind of observational astronomy. I love it. Do you have any more for us?
Oh, well, dark matter. You can't mention dark energy without mentioning dark matter.
Then you just mentioned it. Begin. Proceed.
I guess it started with Vera Rubin going out and while working on her graduate degree, measuring rotation rates and finding no, doesn't match the mathematics. You can add up all the luminous light, and different experiments have shown that this works if you're looking at spiral galaxies doing the spiral galaxy rotation thing. If you look at a variety of galaxies in a galaxy cluster, no matter what it is that you're looking at, the things in the outskirts of the system are moving way faster than our predictions that add up all the luminous stuff, way faster than our predictions say they should be moving. So this meant that there had to be stuff out there, stuff permeating our whole galaxy, permeating all of galaxy clusters, in fact, permeating a lot of space, stuff that we can't see via the electromagnetic force. And that's just perplexing and difficult to think about. And again, expectations failed. The idea that there'd be something that didn't reflect light, didn't emit light, that was just out there being a gravitational sock. Well, we didn't predict that, but it's sure out there. And over the decades, over the scientific generations of discovery, we've been able to figure out it's at least in part, perhaps not all of it, but it's at least in part some sort of a particle that we haven't fully identified yet.
Yeah. And I mean, the thing is like, with dark energy, I mean, we know a little bit more about dark matter than we know about dark energy, in that what we know with dark matter is that it's probably not gravity. It's probably some kind of particle, and we probably have a sense about, I guess, what its cross section is, how big it is, but that's kind of it. And we know that it doesn't emit electromagnetic radiation, but that's about it. Dark energy, we're like, you know, it's just like, we know it's there, and that's all we got.
Yeah, and sometimes that's all the universe gives you. This is why we keep doing science and keep building new and fancier detectors to do new and interesting experiments to try and figure out not just what this crazy stuff is, but to keep looking for, well, our greatest discoveries seem to keep coming out of this expectation failed.
One of my favorite conversations to have with space scientists, some of the people that are running, like the principal investigators for various missions, like, you know, you talk to the people who are working on the Dawn mission or the people working on New Horizons, and when they do the mission, they have a bunch of stuff that they're looking for, but I think the part that tickles them the most is the stuff that they weren't even expecting. And so now we see these close-up pictures of Pluto, and we see these amazing mountains of ice and these plains of ammonia and methane. this weird hydrological cycle. When we look at Ceres and we see these bizarre salt deposits at the middles of these craters, it's like every time that a new instrument is created that gets out there and is actually able to start taking a look at a new region of space or with more sensitivity, it turns up these surprises. There's one we talked about, the expansion of the universe. There's one great story that I know you probably know from heart, and this is the radio telescopes back in the 1950s that were working on
Microwave.
Yeah, on microwaves.
Right. So people always teach little kids that when you make a discovery, it's a eureka moment. But I think most discoveries that are unexpected like this are actually deeply rooted in the, wait, that shouldn't have happened. What did we do wrong? And for two gentlemen working at Bell Labs, Penzias and Wilson, they were trying to basically plot out what is all of the interference in the microwave band that people building receivers for commercial communications would need to worry about. So when Penzias and Wilson built their big horn and discovered that there was essentially this background noise, no matter what direction they pointed their detector in, the first reaction was, what the heck? Where's the noise in our electronics? What did we do wrong? Is there something wrong with our horn? There was a great deal of scrubbing of pigeon poo, as one does.
Yeah.
And the truth was, no matter how much pigeon poo they cleaned out of that horn, that noise was still there, because the noise is part of our universe. And what they had discovered, what their expectations had failed to account for, I really love Error Code 418, what they'd failed to account for is our universe has this constant background of microwave light that had actually just been predicted by folks working up at Princeton University as being one of the natural outcomes of having a Big Bang, of having a singularity that expanded out from a hot, bright everything into the universe we have today. So what they found was something that, well, a few people had started to say, well, this is something we should detect, but it wasn't generally in the list of things that were being looked for. And they just happened to find it a little bit ahead of their time.
Yeah. That one's a great one. Okay, are there any like fairly recent ones that spring to mind? Events?
Pluto?
Pluto? What, that Pluto exists?
Well, no, we knew Pluto existed, but it should not have active tectonics. I don't think any of our basic expectations of what Pluto should look like came anywhere near reality. We had expected this ancient poxmarked world that was just gouged up with craters and fairly flat other than what was created by the craters. Think moon, but icy. And what we found instead was something that is geologically alive, that has active resurfacing, that has some sort of a heat generation mechanism that is causing convective cells. This so broke with all expectations that there's probably going to be literal generations of researchers dedicating their lives to trying to model how do you get what was seen in that far too swift flyby. And unfortunately, it will probably be the next generation of astronomers that finally gets us to return to that icy world.
Yeah. And I mean, we're starting to run out of time. We could do this all day long. We've got hot Jupiters. We've got pulsars, quasars. I mean, there's so many things that turned up completely, unexpectedly, and even some modern stuff. This could go on forever. And I think, when I talk to the anti-science people, a lot of the time, they say like science is like a religion, and you don't. You won't, you're not open-minded, and you don't And I think that's ridiculous
Yeah.
because so often these outcomes happen, these discoveries are made, they completely change people's expectations and their theories on what they thought they knew and what they understood. And the scientists just go, okay, well, this is the new world now. Now I understand it a
Right.
little better. My old way of thinking was stupid and didn't fit, and I have rejected it. And now I am thinking about this the new way. And they're open-minded. And there's so many examples of these.
Neutrinos. We never talked about how neutrinos change flavors.
Yeah, yeah. We could go on and on and on. So that was the point that I think, there are so many of these events that you make one observation and it overturns the current understanding of the world and the universe as you knew it, and you're into a new one, and that's great. And scientists love it. They love to be wrong.
And I think it's important to know that our great discoveries come from moments of, that's not right. And discovering we're what's not right, because the real universe is far more interesting than anything we can imagine.
Yeah, we just didn't understand it yet. Well, thanks, Pamela.
My pleasure.
So stop
And
that
now
recording.
we save.
Stop this recording up here.
Oh, yeah.
Crazy Chad.
Yeah, stop this.
Yep.
Yeah.
Yep. And then we'll export it here. Let me just do that. Talk amongst yourselves, everybody, while we make sure that we save. What is this? 4? Right. It's right. It's 4:17.
417.
Yeah. Cool. All right. And then I will export to be nice and safe. Haven't explained this part of the project to Chad yet, so okay. How did you like Chad throwing up all those pictures? Did you see all the stuff that we had, like a whole bunch of cool pictures, live, completely unscripted, all coming together?
I was only seeing the bottom three inches, or the bottom, I guess, 20% of them, just because of the way my screen was arranged.
Right.
I wouldn't be distracted, but it was pretty cool.
Yeah, it was cool. People were he was finding lots and lots of cool pictures while we were doing the show. Apparently, you also need an engineer. Tom Nathy was talking to himself. Okay. Zach Cody asks, did Mercury push us towards relativity, or would it have taken longer to figure out if there was no Mercury?
No, I think Einstein would have gotten there he would have just gotten there.
Right. So
Einstein was just kind of one of those special cases.
Right.
Sort of like Chandrasekhar figured out that white dwarfs exist from first principles.
Yeah.
Einstein sort of did the same thing.
Right. Okay. John Suffield asks, after the second discovery of gravitational waves, does Pamela still dislike LIGO?
I withhold judgment at this time.
All right. What about when there's another detector built and another detector, and they're pinpointing the location of these black hole mergers? And
when they come up with utterly novel science, I will
Right.
be less grudging. They're just so expensive. It kind of hurts my heart.
yeah.
If you look at the science per dollar, I'm guessing that their science papers, so the 2 detections they've had so far, are perhaps the 2 most expensive papers written other than about neutrinos.
Right. Well, when they get a third and a fourth, the cost savings will bring it into, it'll come down. Someone asked, Eric Knapp asked, are there places in the Earth where the Milky Way is not visible, being too far north or south?
No, because
No.
it wraps all around us. We're
Yeah.
embedded in the disk. So there's different parts of the Milky Way that you can't see from different places.
Yeah.
So for instance, if you're in the southern hemisphere, there's this amazing dark cloud band that kind of looks like a donkey or an emu, depending on the rotation of the sky, which is just kind of cool. And I can't see that from where I live right now.
Yeah. And the thing to keep in mind, right, is that the Earth is embedded in the plane of the ecliptic. The Milky Way is off at about a 45-degree angle. So it's not like like they're lined up, and you won't be able to see the Milky Way, looking down over the horizon of the Earth, because they're like a cross.
Yeah.
So, is the stream offline?
I don't know. Oh, hold on here.
Yeah, that one.
10 tier.
Let's see. Let's see if there's any more questions. So go ahead and put any questions you've got in the chat. Okay, Margot Robinson says, I happen to think that the reason the Big Crunch was more emotionally satisfying was that it held the hope of triggering another Big Bang and the rebirth of the universe. So I think that makes sense.
True. Yeah.
Better to have total destruction and rebirth than just a sad, disappointing, expanding, cooling forever.
And bounces are always happy. Unless you're playing like dodgeball and it's your face.
I don't know though. Like we're the ones getting smashed up in that collapsing universe. So I'm not a fan. Let's see. Any more questions? Margot Robinson also asks, is there a question of whether dark energy can convert to dark matter or vice versa?
Yeah, they're two totally separate things.
Yeah.
Ignore the fact that they both have the word dark involved. Just ignore that. We should not be allowed to name things. It's true.
Yeah. So Larry Beckham asks, since it doesn't interact with electromagnetic radiation, can dark energy equal? Yeah. So this is the question, right? Dark matter. So they're not dark matter equals MC squared, right? Is there any? No.
So wrong way to think about it. The matter that's in dark matter can be turned into energy. That's not a problem. It's simply, as it is hanging out in the universe, it's not undergoing interactions with photons. And all interactions with photons are mitigated by the electromagnetic force. So because dark matter doesn't interact with photons, the stuff is invisible and annoying.
Let's see. Any more questions? Damien Reloaded asks, could neutrinos be dark matter?
They're part of dark matter, but they're not like the 90% of it. They're a couple percent of it.
Not enough.
Right. So that was a thought for a while, was maybe heavy neutrinos do it, and doesn't quite do it.
Yeah. Lillian Brennan wants to know,
when can we get updates
about the eclipse? Yeah.
So I was really hoping to have that this week, but we're hitting end of fiscal year closeout at my institution, and the poor individual who I have to find out eclipse details from, because she knows the people at the hotel. She's been in budgetary hell, and I like her. So hopefully next week I'll have something. I will at least be able to say, this is the hotel we're in. I don't have prices. I suspect that's where I'm going to be at, is here's the max amount it's going to cost. Here are some alternate places, but I don't have details yet. And I'll get a newsletter. I can get a newsletter sign up for information up. I'll do that.
I guarantee you, when we've decided what's going to happen and we know all the information, we will yell it out from the treetops everywhere and on every social media and on every distribution platform we have access to. So hang tough. Let's see. There was a good one here. Krzysztof Wierzbicki asks, do gravitational waves always go with the speed of light? Apparently. Gravitational waves, speed of light. Yes.
We think so.
Yeah, it'd be interesting if we didn't. One of the things, we just finished up the weekly Space Hangout, and we talked to a bunch of people from the LIGO team, and sort of one of the questions is, what kind of interactions happen between LIGO and some of the other, like the neutrino detectors? And that would be a really fascinating thing, right? Where you detect the black hole collision, and then you look for streaming neutrinos to come from the environment around them. And if they arrive at the wrong time compared to what the gravitational waves tell you, or what visible light or whatever tells you, then you might start to have some questions about gravitational waves. But then that would mean that everything else that Einstein predicted was, he predicted that gravitational waves have to move the speed of light. So
yeah.
David Joseph Wesley asks, is NASA planning a big ramp up for Juno's arrival at Jupiter?
Yes, I should know more about it than I do. Stay tuned to CosmoQuest. We will have articles on our blog and on our social media.
Yeah, and of course we're going to be posting all kinds of stuff on Universe Today as well. We're not long too, like 2 weeks away,
Yeah.
July 4th. We're getting close. So prepare yourself. This is the big one. This is going to be super exciting. I mean, it's no Europa mission, but it's still going to be pretty great. It's no sailboat on Titan, but you know.
And I'm messaging the person who has information about the eclipse in the background just to make sure that you get that.
John Suffel asks, we know that the universe is expanding faster than the speed of light, but what immediate effect will that have on our solar system? So, I mean, there are regions of the universe where they are receding away from us or will recede away from us in the far, far future that it will appear from our perspective to be faster than the speed of light.
And it's not that they're moving faster than the speed of light. It's that the expansion of the universe is causing the stuff between us and them to carry them away faster than the speed of light, which is physically actually entirely different. It's sort of like at the hotel, the little old lady who can move faster than me because she's moving on the moving walkway and it's increasing her speed, and I'm walking not on the moving walkway.
Right.
So with the aid of an expanding universe, you can appear to go much faster than you're actually moving relative to space-time.
Right, but the sort of the point with that is that what, you know, we will see these galaxies, you know, are billions and billions of years in the future. We will see these galaxies sort of redshift away on the cosmic horizon and then fade away into nothingness. But it won't really have any impact on the solar system itself. It's not like the solar system is expanding. It's a cosmological thing, not a local thing.
Right. When I was a weird small child, and I'm going to preface that with the word weird, I somehow learned about the expansion of the universe when I was like in first grade. And I was deeply worried that by the time I was grown up, the expansion of the universe would have made it so that the neurons in my brain couldn't talk to each other. And I was deeply worried about this.
You were a weird little kid.
I prefaced it with the word weird.
Yeah.
And so this was like one of those things that kept like little 6 and 7-year-old me up at night. And then eventually someone explained to me that we're like chemically bound. And so it wasn't a problem.
That is awesome. So to answer, so David Joseph Wesley asks, is there a level of scale where the universal expansion has no effect, molecular atomic? It's galactic. It's galactic clusteric, right? That, you know, the expansion of the universe is having no impact on our interaction with the Large and Small Magellanic Cloud or with Andromeda, right? With the local group, it's not really carrying. We're all gravitationally bound to each other. It's only when you get hundreds and hundreds of millions of light years away is this, you know, are these things, dark energy is taking over and carrying them away from us. So don't worry about your neurons, David. They're fine. We hope. Sean Kenny asks, have you guys ever investigated using nanobots in space exploration? I want to send them to Enceladus.
I personally have not.
Well, okay, so there's this recent idea about the star shot, right? Which are these, you know, we talked about.
Fabulous idea.
Yeah, and they're small. They're not nano, but they're small. But I mean, a nano spacecraft, you know, something as large as a postage stamp or maybe even smaller than that with a teeny tiny little solar sail. I think that's a fantastic idea and a fantastic way to explore the solar system. I mean, they were saying, like, we're going to use this to reach Alpha Centauri. Why not reach Enceladus with one of these, right?
It feels a little bit about the experiments where they've there was an accidental experiment that is by far one of my favorite experiments, where there was a load of rubber duckies that got inadvertently dumped into the ocean, and they've been tracking ocean currents by where the little rubber duckies wind up. There's also all about the British Isles, Northern Europe, and Scandinavia. Similarly, Legos washing up on shore from a different spill. It feels like these experiments that actually allow you to understand solar wind better, understand perhaps eddies that occur behind the shadows of asteroids and such. Um, the kind of thing that you're talking about, the microcraft with microsolar sails, is really just the throwing rubber duckies into the ocean kind of an experiment.
Yeah, yeah. So I have a laser array up in space and just go zip, zip, zap, zap, and it would just zap these little spacecraft off into these various directions. And maybe you get enough of them out there and they can start to communicate with some kind of weird little mesh network. I think it's some really neat ideas. And so it's so weird to me that they describe this really, and I'm sure they're going to test them like crazy in the solar system, but it feels like that's where these things are really going to give us a lot of benefit.
The problem is that you have this 1/r² rule for signals. And so something that tiny simply doesn't have, with any known energy source, the capacity to send a signal back to Earth. And we would have to saturate our solar system with them to the point that it would probably be unsafe to fly humans about. And I'm not sure we really want to saturate our solar system with a mesh network of micro robots. So I'm kind of thinking that while it might make for a really neat art project kind of thing of send them out and then gather them up later, it has the potential to first essentially be biological warfare on the rest of the solar system. And also just not be the kind of thing that has scientific return to it. Sending one to Alpha Centauri, the idea isn't to get a signal back, it's to say, hi, we're here. And that's really what these little micro things are good at doing.
Well, I think the folks at Enceladus need to know that we're here as well. I think, should we really say hi to the Alpha Centaurans without saying hi to the Enceladans? Come on. All right, so Arjone asks, if you were in the Eridanus supervoid, would you get ripped apart? So if you were at this region with galaxy clusters all around you pulling equally, would you get torn apart?
No, because you're chemically bound together much more strongly than the gravity would be pulling on you.
Yeah, I mean, if you were dropped into the middle of the Earth and the middle of the Earth wasn't super hot, you would just float. You'd be in free fall. You wouldn't be torn apart. You would just be floating around. So if you're in one of these big voids, you would just be in free fall. We actually did a great episode on voids with Paul Matt Sutter. So if you go do a... Paul Matt Sutter. But if you do a search, that's because that way if you say Paul Matt Sutter, remember, then that gets his Twitter address properly.
I heard you say Paul Matzer.
Paul Matzer. We have also done a show with Paul Matzer. I don't recall it though. Right. So anyway, we did an episode with Paul Matt Sutter and just talked about cosmic voids and covered a ton of subjects. So if you do a search in Astronomy Cast for the episode with Paul, you'll turn it up and give it a listen. We don't have a video for it. We just have the audio, but it was great. Well, I think we sort of reached the end of our hour, so we should probably wrap things up. Did you have any more announcements? Any more that you want to talk about?
Nope. If anyone has any ideas on how we can do a show on how we're a teapot, we're all ears.
Yeah. I'm sort of going the philosophical route, but I'm playing Stellarium, which is sort of made by the people that make Europa Universalis. Some of you have no idea what I'm talking about. Others of you are nodding sagely, and some are actually excited. But there is an event in that where you discover a teapot orbiting a star, which is is it Bertrand Russell's teapot?
Yeah,
is that the one?
it is.
Yeah. Anyway, so that's sort of, and so that is a sort of skepticism conversation which we could have. as opposed to, teapots randomly appearing in the universe, which would be a quantum mechanics conversation that we could have and talk about Boltzmann brains and talk about how the universe can perceive itself.
Teapots will be involved in the next episode.
Teapots will be involved. I can't believe you literally justified the whole concept of episode 417 by searching up what 418 was. And you know what I mean? And it was a completely unexpected result.
Yes.
And you were then forced to sort of have
embrace
a brand new description of the universe that you perhaps hadn't thought of before. So there you go. As a scientist, you're ready. You were ready for a error code. Yeah. All right. Well, thanks everyone for watching. Thanks, Pamela, of course, for bringing the brain. We do appreciate it. And we look forward to next week's episode, 418, something to do with teapots, before we wrap up this season and take a much needed break. So thanks everyone for watching, and we'll see you all next week.